Alright, so in today's tutorial video, I want to look at statistical methods for analyzing two-sample data in STATA. But before we proceed, I'll urge you to kind of take a look at my previous tutorial video on the flowchart for classifying data, okay? Because in that video tutorial, I illustrated and explained the data structure for two-sample data, which will help you to catch up with everything that I'm going to do in today's tutorial video, okay? You can just check on the link in the card above or check the link in the description of this video. Alright, so now let's begin. Like the one sample data, we have parametric tests and non-parametric tests for analyzing such data. The same applies with two sample data. The type of parametric test for two sample data is known as the TwoSample Ttest or the independent T-test. Okay, this test basically compares the means of two separate groups to determine whether statistical evidence shows that the associated population means are significantly different. Okay, for example, researchers may wish to compare the mean income level of two regions or the mean effectiveness of two drugs. Okay. There are certain assumptions which must be satisfied before we can make use of this test. One of the assumptions is that the data must be continuous. The next one is that the two samples are independent. The third one is that the data must be normally distributed. And the fourth one is that the variances of the two populations are equal, okay? This condition is necessary because even if it is not satisfied, we can still proceed and make use of the two-sample T-test. We just have to specify in our computation that the variances are not the same, okay? Now let's take a look at the non-parametric test for two-sample data. This is known as the Mann-Whitney U test or the Wilcoxon Rank Sum test. This test basically compares the medians of two separate groups to determine whether statistical evidence shows that the associated population medians are significantly different. Okay. For example, researchers may wish to compare the median income level of two regions or the median effectiveness of two drugs. There are certain conditions which must be satisfied before we can make use of this test. One of the conditions is that the data must be continuous. The next one is that the two samples are independent, and then last one is that the data must not be normally distributed. Okay, now let's take an example. As a researcher, you wish to compare the average sepal length of the T-test and Virginica plants from the average data set. Perform statistical analysis for this data. Okay, now before we jump into our STATA window to begin, let's take a look at the average data set in a CSV format. So this is the average data set in the CSV format, and there's a clean data. Okay, before you analyze any data set, you have to ensure that you have cleaned your data. If you want to learn how to do data cleaning in STATA, you can just check out my video on exploratory data analysis in STATA. Okay, you can just click on the link in the card above or check the link in the description of this video. Okay, now the problem here is to find out if the sepal length for T-test, the average value of the sepal length for T-test is the same or different compared to the average value of the sepal length for Virginica. Okay, so what we are going to do is to first of all filter the sepal length for T-test, which starts from here and ends somewhere here. Okay, it ends. Okay, that's the end for T-test. Then try to filter the sepal length for Virginica. Okay, so Virginica starts here and it ends somewhere here, I think to the last one. Alright, and try to find out if the average value for this is the same or different compared to the average value of the sepal length for T-test. Okay, in other words, we want to find out if the difference in the average value is equal to 0 or it is different from 0. Okay, but in STATA, because we cannot work with multiple data sets at the same time, what we're going to do is to basically remove the vesicular variables from our data set, okay, so that we can have only that of the variables for T-test and that of Virginica. Okay, so let me highlight that of the vesicular, start somewhere here. So I'm going to remove all the variables for vesicular to ends here. Right click on this, okay, delete. So entire row, okay, so that we get only the variables for T-test and that of Virginica. Okay, so we are good to go. So the next thing that I want to do is to basically save this as, let's rename this, save as. So you move to your current folder. Let's try and save this as clean data 1. Okay, this is a new one, clean data 1, and this is the previous one in the CSV format. Okay, save. So yes. Alright, so we can now jump into our STATA window to begin. Okay, so I'm going to make use of a do file. Okay, so first of all, I want to set our working directory. Okay, so this is my current working folder, and I have my previous data set. This is the original one. This is the new one that I've created, which consists of only the variables for that of Virginic and that of CTOS. Okay, so I'm going to make use of this. So this is the path. Just click on here to get the path and copy this. Yours may be different from mine, okay, depending on where you save it. So I'll leave this data file in the description of the video so that you can download it. Okay, so now let's go back to our do file. So then you paste it in double quote. Okay, so here's mine. So I've pasted it in here. Then can execute this. Control D. Okay, let's see the effect. Okay, so now we can proceed and import our data set now. Okay, alright, so I'm going to use the import delimited because it's CSV format. Let me highlight this. So this is the name of the data, clean data1.csv, and I want to clear if there's any previous existing data set in STATA memory. I want to clear that and make use of only this one. Okay, let's try and execute this. Control D. Okay, let's move to our result window. Okay, so we can see 5 variables and 98 observations. So let's view our data set by making use of the browse function. Let me highlight this. Control D. Okay, so this display our data set in a spreadsheet form. Okay, similar to the one we saw in the CSV format. Alright, so let's go back to our do file and get a structure for our data set. Okay, so let's execute this. Control D. Alright, so here we go. So we can see that we have 98 observations, 5 variables, and the data type for sepal length, sepal width, petal length, and petal width, they are all floats, which is basically the same as numeric. But we can see that species is in a string format. Okay, so in our data manipulation, we are supposed to encode this by basically converting the string into numeric, or basically assigning some values to the labels. Okay, so let's quickly do that. So in our data manipulation, we want to convert a string variable into numeric. Okay, we can use the codebook to also get some more detailed information. Okay, so let's execute this. Control D. Alright, so here we go. So we can see that CTOS and Virginic are all in string, but we don't need to have this. Otherwise, we have some challenges in our computations. Okay, so we are supposed to assign some values to the labels. Okay, that's basically what we want to do. So let's use the encode function, which is basically going to help us to get that. So we want to encode a species, and basically we don't want to override the previous name. So we want to give it a new name for this transformation. We want to name this as species 1. So we are using the generate function. So this encode function is basically going to convert or basically assign some values to the labels of the species. Okay, so let's execute this. Control D. Alright, so let's use the describe function to see the effect. Control D. So we can see that now we have another variable being added to our data set, which is species 1, and now the data type is long, or basically the same as numeric. Okay, so let's use the codebook function to get more detailed information with regards to our new variable species 1. Control D. So here we go. So now we can see that 1 has been assigned to CTOS and 2 has been assigned to Virginic. Okay, so now we are good to go. Alright, so we can basically drop our previous species. Okay, this is optional. We want to drop the previous one, we don't need it. So let's run these 2 lines. Control D. So we can see that now we don't have our previous species. Okay, we have only the new one. And the next thing I want to do is to rename the variables. This is also optional. Okay, so let me try it. Okay, so let me add this to it. So I want to rename the sepal length as SL, sepal width as SW, petal length as PL, petal width as PW, and species 1 as SP. Okay, let's execute this. Control D. So let's see the effect. Okay, so you can see now the variable has been changed. The names has now been changed. Okay, Alright, so the next thing that I want to do is to basically do some exploratory data analysis, okay, to find out whether we are going to make use of the TwoSample Ttest or the Mann-Whitney U test, okay. But this will look similar to the one that we did under statistical methods for analyzing one sample data in STATA. So in order to repeat the same process, I'm going to skip the exploratory data analysis for now, okay. If you want to look at how the exploratory data analysis was done, you can check out my video tutorial on statistical methods for analyzing one sample data in STATA, okay. From the exploratory data analysis, we got to know that the distribution of the sepal lines for T-test and that of Virginica were nearly symmetric, right? So the next thing I want to do now is to basically test for the assumptions, okay? For parametric test, one of the assumptions is that the data must be continuous, okay? So if you check this, you can see that the values of the sepal length are already continuous, okay, and they're also independent, because if you look at Setosa, it's different from Virginica, okay. So the second assumption is also satisfied, okay. So basically we have two different groups here. One is Virginica and one is Setosa, okay. So basically they are going to be independent, okay. Then the third assumption is to check for the normality, okay. So let's go back to our do file. So to test for the normality assumption, we are going to make use of the QQ plot. That's the first one. You can also make use of the Shapiro-Wilk test, of course. Alright. So the QQ plot basically draws the correlation between a given sample and the normal distribution. Okay, so that if the data is approximately normal, then the plot will closely resemble a straight line sloping upwards to the right. Okay, so let's get a QQ plot of the sepal lines for Setosa. So I'm going to use a qnum function. Qnum is sepal length if the species is equal to 1, and we know 1 is for that of Setosa. Okay, so let's try and execute this. Control D. So we need to see a window, right, a new window of graphic. So that's basically what we're waiting for. I think it's still compiling. Alright, so here we go. So we can see that most of the points are on the straight line and it is sloping upwards to the right. Okay, so this is an indication that the distribution of the sepal length for Setosa is normally distributed. Okay, let me close this and go back to my do file, and let's get that of the QQ plot of the sepal length for Virginica. Okay, so let me highlight this. Okay, so now species 2. Okay, Control D. Alright, so you can see that some of the points seem to deviate from the straight line, but majority of the points are on the straight line sloping upwards to the right. Okay, so this is one indication that the distribution of the sepal length for Virginica is normally distributed. Okay, and now another test for normality is that of the Shapiro-Wilk test. Okay, so the null hypothesis for this test states that the data is normally distributed. Okay, so let's try and get out of the Shapiro-Wilk test of the sepal length for Setosa. Okay, so I'm going to make use of this function, S-work function. Okay, let's execute this. Control D. Let's check our result window. So here we go. So we are interested in this p-value. Okay, we want to compare this to the threshold value or the alpha level at 1% or 5%. Okay, the decision here is that we are going to reject the null hypothesis if this p-value is less than or equal to the alpha level at 1% or 5%. Okay, so because this p-value is basically greater than the threshold value or the alpha level at 5%, it means that we fail to reject the null hypothesis and conclude that the distribution of the sepal length for Setosa is normally distributed. Okay, now let's get that of the Shapiro-Wilk test of the sepal length for Virginica. So I'm going to highlight this. Okay, this is now for SP2. Okay, Control D. Let's check our result window. So this p-value, if you have to compare it to the alpha level at 1% or 5%, it means that we fail to reject. Okay, because this one is greater than the alpha level at 5% or 1%. So basically, we fail to reject the null hypothesis and conclude that the distribution of the sepal length for Virginica is normally distributed. Okay, so now that we are clear that the three assumptions has been satisfied, we are now clear with the kind of test that we are going to make use of. Okay, so we are going to make use of the parametric test, specifically the two-sample t-test or the independent t-test. Okay, all right, so let's scroll down. All right, so the null hypothesis for this test is that the mean value of the sepal length, right, for the mean value of the sepal length for Ttest and that of Virginica are the same, and the alternative is that the mean value of the sepal length for Ttest and Virginica are different. Okay, in other words, we can also say that the difference in the mean value of the sepal length for Ttest and Virginica is equal to 0, and the alternative will be that the difference in the mean value of the sepal length for Ttest and Virginica is different from 0. Okay, now if you recall, one of the assumptions under the two-sample t-test was in asterisk, okay, which states that the two population variances must be the same. Okay, so we have to basically test for that before we start with the two-sample t-test. This is called the test for homogeneity of variances, and we are going to make use of the 11E test. Okay, so in STATA, the 11E test can be used, or we can make use of the 11E test by using this function, the Robover function. Okay, alright, so let me highlight this. So the Robover function is going to help us to get the equality of variance, which is similar to the 11E test. Okay, this is the continuous variable sepal length, and this is the group. Right, we have two groups. One is for Ttest and one is for Virginica. So let's try and execute this. Control D. Alright, so let's jump into our result window. Okay, so here we go. So we have some test statistics with their corresponding p-values. This is basically the test statistic of the 11E test for the test statistic for the 11E test centered at the mean. Okay, and this is the corresponding p-value, and this is a test statistic, right, for the 11E test centered at the median, and that's the corresponding p-value. And this is also the test statistic for the 11E test centered using the 10% trim mean. Okay, this is basically means that the top 5% and the bottom 5% of the values are trimmed out so that they don't overly influence the test. Okay, and that's the corresponding p-value. Okay, so let's try and use the p-value for to make our decision. So we already reject the null hypothesis if this p-value is less than the alpha level at 1% or 5%. Okay, now if you have to compare all this p-value to the threshold value or the alpha level at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that the variances, right, for that of the sepal length, right, for Ttest and that of Virginica, they are different. Okay, so basically the variance are not the same for these two groups. Okay, so now that we are clear that the variances, right, are not the same for these two groups, that is for Ttest and that of Virginica, we can then proceed and make use of the two-sample t-test. Okay, so let me scroll down. So in here, I'm going to make use of the two-sample t-test. So this is the function t-test, the sepal length, and the group is species. By default, it assumes that the variances for the two groups are the same. Okay, but from our analysis, we have obtained that the variances are not the same. So that's why we have an equal here. Okay, so let's try and execute this. But before that, one thing that you have to note with regards to the t-test is that in books it is required that the sample size should be less than 30. Okay, but one thing that you have to note with regards to the two-sample t-test is that it is a symmetric distribution or a family of curves that is based on the concept of degrees of freedom. Okay, and this is related to the sample size. So as the sample size increases, the t-distribution approaches the standard normal distribution. This is related to the central limit theorem. Okay, so even if the sample size is more than 30, we can still make use of the two-sample t-test. Okay, So let's try and run this. Control D. Let's check the results. Alright, so here we go. So we have the mean value of the sepal length for Setosa, and we have the mean value of the sepal length for Virginica. Alright, and this is the difference. I want to find out if the difference in this mean value is equal to 0 or it is different from 0. Okay, now if you look at the result from the p-value for two T-test, we can say that this p-value is less than the alpha level at 5% or 1%. So it means that we are going to reject the null hypothesis and conclude that the distribution of the sepal length or the mean value of the sepal length for Setosa and that of Virginica are not the same. In other words, we can also say that there's enough evidence to indicate that the difference, the mean value of the sepal length for Setosa and that of Virginica is different from 0. Okay. Alright, so now let's assume that the normality test failed. If the normality test failed, then we are supposed to make use of the non-parametric test, basically make use of the Mann-Whitney U test or the Wilcoxon Rank Sum test. Okay. So assuming that the normality test failed, then with the same process, we are just going to make use of the Mann-Whitney U test. Okay, that's going to be the non-parametric version of it. So we are going to make use of the rank sum function. Okay, and so I think this is the first argument, that is the sepal length, and the second argument is that of the groups. Okay, for Setosa and that of Virginica. Alright, so in books, one thing that you also have to note is that it is required that the sample size for this non-parametric test, that is the Mann-Whitney U test, be less than 30. Okay, but you are going to ignore it for now. The procedure for this test involves pulling observations from the two samples into one combined sample, keeping track of which sample each observation comes from, and basically ranking the lowest to the highest from 1 to the last element of the combined sample. Okay, that's basically the procedure for this Wilcoxon Rank Sum test. Okay, so let's try and execute this to see the result. Control D. Alright, so let me see. Alright, so we are interested in the p-value here, okay, to make our inference. So if you have to compare this p-value to the alpha level at 1% or 5%, it means that basically we are going to reject the null hypothesis and conclude that the median value of the sepal length for Setosa and that of Virginica are not the same. In other words, we can say that there is enough evidence to indicate that the difference in the median value of the sepal length for Setosa and that of Virginica is different from 0. Okay, so this is basically how to perform a detailed statistical analysis for two-sample data in STATA. Please, if you found value in this video tutorial, don't forget to subscribe if you have not, and also turn on the notification bell to get more updates anytime I post on this channel.